Okay, so let's talk about linear systems and elimination. And when I say a linear system, at least for now, I mean like an algebraic system. So this is not a linear differential equation. It's like this. If you're in differential equations class, this is probably review. You've almost certainly done things like this before, but so bear with me here. I'll try to go fast. So let's solve this. I've got two equations and two unknowns. So here I want to eliminate x from this one. So I'll call this equation 2, and I'll subtract 2 times equation 1, and I'll stick that here. So let me turn this into, so nothing happens on the first equation. 2x minus x is 0. Y minus 2y is minus y. 4 minus 2 times 3 is negative 2. And so now I'm going to have my answer. So this one tells me y. And once I know y, I can plug that in up here. So I got both of my variables. Great. So here's a couple of other things that can happen. So in this one, everything was pretty nice. We got definite answers for x and y, unique answers. So x can only be one thing, y can only be one thing. But there's other things that can happen. So all I did to get the next one is I put a 2 here instead of a 1y, and that's the only difference. So let's do this now. Well, I would try the same thing. I would do equation 2 minus 2 times equation 1, because I still want to eliminate x from this equation. And what happens? Now 2x minus 2x is 0. 2y minus 2y is also 0. 4 minus 2 times 3 is still negative 2. And what I've arrived at is a system that's telling me nonsense. Fundamentally, we're looking for values of x and y that make these equations true. And there is no value of x or y that could ever make this second equation true. 0 does not equal negative 2. So since there's no possible value of x and y that makes this true, we say no solution. So we have to accept that if it says solve and it gives you a linear system, sometimes there is no solution. We have to accept that that's a possible answer. Of course, my instructions are a bit brief, so maybe my instructions should say solve or else say that there's no solution, but I like to be brief. One more thing that can happen. Here's a very similar system. This is just like the last one, except I changed that there used to be a 4 here and now it's a 6. So bear with me. We do the same thing. We would want to eliminate x from this. And so what am I going to do? So first one stays the same. And now everything is 0. This tells me 0 plus 0 equals, and 6 minus 2 times 3 is 0. So we're in a very different situation. Any value of x or y makes this equation true. So this second equation is not really contributing anything to my knowledge about x or y. This is automatically true. The only relevant information I have about x or y and y is that x plus y equals 3. And really, maybe I should have known that from the beginning, because even if I look at the original two equations, the second one is automatically true if the first one is true. The second one doesn't contribute any new information. Like if x plus y is 3, then of course 2x plus 2y is 6. It's just doubling everything. So what can we do? We just ignore the one that doesn't contribute anything. And what's going to happen is there's going to be infinitely many solutions. And what's the best we can do to describe this? One way of describing it is, so I can solve it for x. Of course, I'm not going to get a unique answer. It's going to depend on y. And y could be anything. And let's say we're solving this over the real numbers. Sometimes we're going to talk about complex numbers, but for today, let's assume that everything is, oh, I accidentally made it plural. Let's say for today, everything's a real number. So we also have to accept that sometimes systems are like this. We do have infinitely many solutions, and then the best you can do to describe a solution is to say, well, there's going to be certain variables that could be anything, but you can still solve for the other ones in terms of, like we solve for x in terms of y. Okay, so I used 2x2 systems because I wanted to illustrate these things really quickly. Of course, we're going to talk about 3x3 systems and kind of like anything by anything systems in general. So let me talk about some theory here. So there's this form that we can get a system in called echelon form. A linear system is in echelon form if each leading variable, and the leading variable is the first one with a non-zero coefficient, and when I say the first one, I mean from left to right. So if I'm looking across an equation, there's going to be certain coefficients that are zero, like say here. I would say that y is the leading variable in this one, x is the leading variable in this one. And so we say it's in echelon form if each leading variable is to the right of the leading variable in the row above what we're looking at. Unless we're at the very top, and then there is no row above what we're looking at. So there's no requirement for the very top. Also, any equations that have all zero coefficients should be at the bottom. So, for example, here this is a system in echelon form because, well, there's no requirement for the top row because there's like the leading variable is x, but there's no row above it. I'm using the words row and equation sort of interchangeably here, by the way. So when I point to this equation, I'm calling it a row. But the point is, the row that has all zero coefficients is at the bottom. So more generally, what can echelon form look like? Basically, I should be able to draw some stairs, and each time I go down, like basically this is a leading variable, and then I go across until I reach the leading variable in the next row, which should be to the right. So it's like I'm going to the right, and then I go down, and then I can go to the right until I reach the leading variable of the next one, and then down, and then I have my all zero row at the very bottom as it's supposed to be. But why am I drawing these stairs? Just sort of a visual representation. Notice that the leading variable is supposed to be to the right, so as I go down, I'm going to go to the right. I'm not going to go to the left. I shouldn't have a leading variable like below and to the left of this leading variable. I am allowed to take multiple steps to the right, so I might be going to the right for a while until I find my next leading variable. I'm also not going to take 2 steps down in a row. Like, I wouldn't go down 2 rows like this because that would mean that this leading variable is directly underneath the leading variable in the row above, which it's not supposed to be. It's supposed to be strictly to the right. Yeah, so that's what echelon form is, and that's basically what we're going for when we do elimination. Like, if I had an x down here, then I would want to eliminate x from this by subtracting a multiple of this equation. when I'm eliminating these variables, I am getting it in echelon form. Like in all three of the examples that I did, I wasn't using the phrase echelon form, but that's what I was getting these systems in. So, this is called Gaussian elimination because I guess Gauss invented it. This procedure of eliminating variables from equations below and getting it in echelon form as a method of solving a linear system. So here's a sort of a high-level description of how this goes. You get your system in echelon form using what we call row operations, and these row operations are like what we were doing. The basic row operations, and yeah, again, row just means equation here. I can take an equation and multiply it by a non-zero scalar, like I can take the whole thing and multiply it by 2 or 3. I shouldn't multiply it by 0 because then it's just like I'm going to lose information because it's just going to tell me 0 equals 0. I don't want to lose information if I have an important equation. So, but I can multiply it by any non-zero scalar. I'm also allowed to just swap two places, like if there's an equation on the bottom and I wish it was at the top, then I can swap it with the one at the top. And I can also add a row to another row. By the way, in the way we do this, I often do at like 2 of these at the same time, like in this step when I did equation 1 minus 2, or sorry, equation 2 minus 2 equation 1, that's basically doing the first operation and the third operation at the same time. So it's like I'm taking equation 1 and I'm multiplying it by -2, so that's like the first operation, and then I'm adding that to equation 2. So we often do multiple ones of these at the same time, but just to break it down into single operations, we are allowed to do multiple ones in one step, but these are the things we're allowed to do. Okay, so you get it in echelon form. Then the first thing I would do is look at the very bottom, because any equations that have all 0 coefficients should be at the very bottom. If you see anything that says 0 equals non-zero, like this example where we had 0 equals -2, then we say no solution. If every variable is a leading variable in some equation, then there's a unique solution. And that's like the first example that we did. And here's what I mean by every variable being a leading variable in some row. X is leading in this row. Y is not leading in this row, but Y is leading in some row. So every variable is leading in one row. And we got a unique solution. We got a definite answer for X and Y. We didn't get infinitely many or anything like that. Otherwise, there's infinitely many solutions. And that is like, where did it go? Yeah, that is like this one. In this one, we have our zeros at the very bottom, so that's fine. But this doesn't say 0 equals non-zero, so I'm not going to say that there's no solution. This says 0 equals 0, and that's fine. But not every variable is leading in some equation. X is leading in this one. Y isn't leading in anywhere. Y isn't leading up here. Y isn't leading up here because Y has a 0 coefficient. So Y isn't leading anywhere. And so this is how we got infinitely many solutions. By the way, in the example that we did from the last page, this has infinitely many solutions. I do have an all zero row, but that just says 0 equals 0, so I can ignore it. And so let's check the leading variables. X is leading up here, Y is leading up here, Z is not leading anywhere, W is leading here. But so it's not the case that every variable is leading in a row. Z is not leading in any row. So what can we do? We can still pull off something like we did in the easier case, the 2x2 case that had infinitely many solutions. There's going to be a variable that can be anything, and we can at least solve for the other variables in terms of the variable that can be anything. So W, I am going to get a definite answer for. I can just solve this for W, so it's 7/2. So I can plug that in up here. What I'm going to do, the variable that isn't leading anywhere, I'm going to make the free variable. That's the variable that can be anything. So I'm going to say Z can be anything, and I'm going to solve for everything else in terms of Z. So let's see how much trouble I got myself into with these fractions. 8/2 plus 7/2 is 15/2 minus Z. So Y is 3/2 minus 1/5 Z. So like I said, I'm solving for everything in terms of Z. W doesn't even depend on Z. I got a definite answer for W. Y does depend on Z. And I should be able to solve for X in terms of Z as well. So I'm just taking this first equation and I'm plugging in what I know about W and Y, and I don't know anything about Z. Z could be anything, so I just leave Z as Z. Oh, and that equals 3. And there's, yeah, well, okay. I made this example up, so I should force myself to do it. X minus 3 plus 2/5 Z plus 3Z plus 35/2 equals 3. The fractions are annoying, but it's not that bad. Let's collect like terms. X. Let me combine my Z. So I've got 17/5 Z. And then, so this is 6/2, so I've got 29/2. Okay, so X is, I've got 6/2 minus 29/2, so that's going to be negative 23/2 minus 17/5 Z, and that's what X is. So it's a little painful, but so like I said, we can solve for every other variable besides Z in terms of Z, and Z could be anything.